What's up, everyone? Welcome back. Patrick here. Moving on to the next question dealing with quadrilaterals. So we are given a quadrilateral that has these vertices a -3 and 1, b 4 and 2, c 9 and -3, and then d 2 and -4. And then we have to answer these questions dealing with that specific quadrilateral. So we got to verify that it's a rhombus. And I'm going to go through what a rhombus is and the particular properties that it has in a second, just a general overview. And then in part B, we have to verify that the diagonals bisect each other at right angles. And then part C, we have to verify that the diagonals are not going to be equal lengths. So let's start off with first discussing how we verify that that a quadrilateral is a rhombus. And the easiest way to verify a rhombus is basically a quadrilateral that has all equal side lengths. That's it. It has all equal side lengths. That's the main property of a rhombus. It's a quadrilateral with 4 equal side lengths. Now, in general, if you draw a quadrilateral with 4 equal side lengths, it could take different shapes, but what's always going to happen if they have 4 equal side lengths, so let's say something like this, right? So this, all 4 are the same, then inherent in that definition, the opposite sides are always going to be parallel. Okay, so you don't have to show that the opposite sides are parallel like a parallelogram. All you have to show is that all 4 sides are equal lengths, and then you prove that it's a rhombus. Now, some teachers may want you to show that the opposite sides are going to be parallel, but if you can just show that they're all 4 equal lengths, then that property there, inherent in that property is that the opposite sides are always going to be parallel. But again, your teacher may want you to show opposite parallel sides as well. But in this particular case, when we verify that it's a rhombus, we're just going to show that all of the 4 sides are equal lengths. Now, here's where there can be a little bit confusion when dealing with a rhombus and squares, because a square is actually a particular case of a rhombus. So staying here in the general rhombus properties, now a rhombus, another characteristic or another property of a rhombus is that the diagonals are going to bisect each other at right angles. That's always going to happen, and we're going to verify that property in part B. So let's write that property here. The diagonals bisect each other at right angles. Okay, for any rhombus. And so we're going to verify that property in part B. Now, as I mentioned, a square is a type of rhombus. So here's where the confusion can sometimes lie. A rhombus can pretty much be split up into 2 different cases. Either it can be a square or it can be not a square. Okay, in a square we know it basically looks like this, right? All 4 sides are equal lengths. And so just that property right there basically proves that a square is a type of rhombus. Now, in particular with a square, what's going to happen is that these angles here, they're all going to be equal and they're all going to be 90 degrees. Okay, so that's what's going to happen in particular with a square. But if a rhombus is not a square, then it's going to take a shape like I had before. It would look like that, for example, where all 4 sides are equal, okay? But notice that the angles, they're not all equal. They're not all 90 degrees, right? So this is the more common type of rhombus that you're going to be working with, but we're also going to do a question where we have to verify that a certain quadrilateral is a square. Now, here is where there's a particular property in terms of the diagonals that differentiates whether something's going to be a square, whether a rhombus is going to be a square or not a square. And in a square, the diagonals are equal lengths. Okay, and if a rhombus is not a square, then the diagonals are not equal lengths. And so notice that in part C, what we're going to show is that the diagonals are not equal lengths. So the type of rhombus that we're going to be dealing with is this kind of rhombus. It's not going to be a square, meaning that those angles are not going to be right angles. They're not going to be 90-degree angles within that quadrilateral. Right? So for both of these, the diagonals still bisect each other at right angles. So if we let's draw a square here. If we draw the diagonals, okay, this is almost like a rectangle. You want to make sure it's really to scale here. Right, that looks more like a square. So if we draw the diagonals, here the diagonals are still going to bisect each other, meaning that this and this are equal lengths, and then this and this are equal lengths. But in this particular case, because we're dealing with a square, the diagonals are actually equal lengths, and so this, and then this, those are all equal lengths right there, okay? And they bisect each other at right angles, like that. Okay, so that's what's going to happen for a square, and again, we're going to go through a video where we're dealing with this particular type of case. Now, if a rhombus is not a square, so if we draw a bigger diagram here, it's maybe, just got to make sure this is really to scale here. Like that, let's say. Okay, so all of these are equal. If we draw the diagonals, notice that they are bisecting each other, okay? What that means is that this length and this length are the same, right? It cuts this diagonal in half, and then this length and this length are the same. But this length and this length are not necessarily, or they're not for sure going to be the same if we're dealing with a rhombus that's not a square. But it's still going to bisect each diagonal at a right angle, like that. So this property, this general property, holds for both. Okay, it's bisecting the diagonals at right angles, but these two properties are specific to each of these cases, where the diagonals are equal lengths if you're dealing with a square, and then the diagonals are not equal lengths. Notice that this diagonal here, it's a bit longer than this one over here. So the diagonals are not equal lengths. When you're dealing with a rhombus, that is not a square. Okay, hopefully that made sense, especially with the diagram. I know it could get kind of confusing, but a lot of times students get confused in terms of a square, a case of a square, and then a rhombus, and where all this fits together. So hopefully this kind of clears up some confusion for you. And that's why I wanted to take a little bit of time to explain this before we get into the actual algebra. And this can also be like a tricky true or false type of question. So you might get a statement saying a square is a rhombus, right? That statement, a square is a rhombus, and that statement is true, right? A square is a type of rhombus. Or you might get a statement saying a rhombus is a square, okay? And that statement is not necessarily true. That statement will be false because a rhombus can also be a quadrilateral that has 4 equal lengths, but it's not a square, right? So you got to be careful. You got to read these kinds of statements carefully. It's a popular type of question that could come up on a test, right? So hopefully this diagram here lets you kind of file things in your mind a little bit better. So let's get into the particular specific question that we're dealing with. And what I'm going to do to start off is draw just a rough diagram of a rhombus that we can have as reference. Okay, now we know that we're going to deal with the case where it's not going to be a square because of part C. We're going to verify that the diagonals are not equal lengths. So we know it's going to take this kind of shape. Now this is not necessarily to scale. Like if you draw this on a Cartesian plane, it might be maybe rotated, shifted around, flipped over, etc., etc. But I'm just drawing a rough diagram that we can have just as reference when we are working through the algebra of these questions here. So in part A, we're verifying that it's a rhombus. So what we're going to do is we're actually going to find the lengths of all four sides, and we just have to show that they're going to have equal lengths. So let's start off with finding the length of AB. Now, the length formula in particular, if you remember, it is x2 minus x1 squared plus y2 minus y1 squared, all square rooted. So we're dealing with AB first, so let's do x1, y1. We'll let this be x2, y2. So we'll have x2, which is 4, minus x1, which is -3. Be careful with the brackets there because we're subtracting a negative number. And then we're going to square it plus the y2, which is 2, minus y1. And then we're going to square it like that. So notice here, 4 minus -3 is like 4 plus 3, which would give us 7. And then 2 minus 1 is 1. And then we'd end up with 49 plus 1, which would give us root 50. And as a decimal, it's going to be 7 point something. I'm just going to leave it as an exact value. So let's keep track of this over here. So the length of AB is root 50. Now let's find the length of BC. So B we already have x2, y2, so I'm going to label C as x1, y1. And so what we would adjust is basically these values over here. So we'll have 4 minus x1, which is 9. Then we'll have 2, y2 minus y1, which would be 2 minus -3. So just be careful, again, with your brackets there. So over here, we'd end up with -5 to the power of 2 plus 2 minus -3 is like 2 plus 3, which would give us +5. And then notice we end up with 25 plus 25, which gives us that 50 under the square root. Okay, so the length of BC is also root 50. And then let's find the length of CD. So we got x1, y1 for C, so let's label x2, y2 for D. Okay, so what's going to change is this over here, right? So the x2 is going to be 2, right? 2 minus 9, x2 minus x1. Then we'll have y2, which is -4, minus y1, which is the -3. So over here, we'd end up with 2 minus 9, which is -7. That's going to be squared plus, let's do this on the side. There's a lot of negatives going on. So we got -4 minus -3, which is like -4 plus 3, which would give us -1, like that. So that bracket is going to end up being -1. That's going to be squared. Both of these turn into a positive. And we end up with that 50 again. Okay, so CD is going to be root 50, right? And then finally, we just have to find the length of AD, right? This side. Over here, so we already have the x2 and the y2, the 2 and the -4. So let's change the x1 and y1. So the x1 in this case is going to be -3. Then the y1 is going to be 1, +1 right there. Okay, so what's going to happen here? We're going to have 2 minus -3, which would be like 2 plus 3, which would give us 5. That's going to be squared, plus -4 minus 1 is -5. That's going to be squared, which would give us 25, plus 25, which would give us root 50. All right, so the side AD is root 50 as well. And so notice that we got all four sides being equal lengths. And so that's enough to verify that the quadrilateral that we're working with is indeed a rhombus. So now moving on to part B, we got to verify that the diagonals are going to bisect each other. So what I'm going to do, just to give myself some room, I'm actually going to erase all this here. So with part B, what we're going to do is we're going to be working with the diagonals. So the diagonals, in this particular case, notice that it's AC and CD, like that. And so what we got to do in part B is we have to verify that the diagonals are first going to bisect each other, meaning that for this diagonal, this point here is going to cut this diagonal in half. So this length and this length are going to be the same. And then for this diagonal, this same point is going to cut this diagonal in half, meaning this length and that length are going to be the same. Right? Even though the diagonals are going to be different lengths, as we're going to show in part C, that point of intersection between them is still going to cut them in half. Now, in part B, we got to do two things. Okay, so we have to verify that the diagonals bisect each other. So that's the first step that we're going to go through. And then the second step is that they bisect each other at right angles. Okay, so we're going to split this up, split part B up into two steps. We're first going to show that the diagonals bisect each other, which is going to be really simple. And then in part 2, we're going to show that they bisect each other at right angles. And then for 2, okay, let's go actually through these one by one. So number 1, all we have to do is we have to show that the midpoint of AC is equal to the midpoint of BD. Right? Because notice that this point here, it's going to be the midpoint of AC because it's splitting it. Right? If we show that this midpoint for this diagonal is the same as the midpoint for this diagonal, then we know that it's that same point that's splitting this diagonal in half and this diagonal in half. And so that's all we have to do for part 1. So in part 1, all we have to show is that the midpoint of AC is equal to the midpoint of BD. All right, and that's enough to show. Now in step 2, to show that they're bisecting at right angles, we have to show that these two diagonals are going to be perpendicular. And so how can we do that? Well, what we can do is we can find the slope of AC, we could find the slope of BD, and then if those two slopes are negative reciprocals of one another, then we know that those two lines, those two diagonals are perpendicular, right? And that means that there's going to be a right angle in between them, right? All of these are going to be right angles, like that. Right? So all we have to do in number 2 is we have to show that the slope of AC is going to be perpendicular to the slope of BD. And so doing these two steps right here would verify that the diagonals of this rhombus, of this quadrilateral, are bisecting each other at right angles. We only have to do those two steps. Right? So just wanted to give a brief overview of the steps involved in case you run into a question like this. So let's first find the midpoint of AC. Now what is the midpoint formula? We add up the x values divided by 2, add up the y values divided by 2. So let's label this x1, y1, x2, y2. So we'd end up with negative 3 plus x2, which is 9. That's going to be over 2. Then we'll have y1, which is 1 plus negative 3, and then that's going to be divided by 2. So continuing this here, we'll have negative 3 plus 9, which is 6. That's going to be over 2. And then we'll have 1 plus negative 3, which is like 1 minus 3, which would give us negative 2. That's going to be over 2, which would give us 3 and negative 1. Okay, so let's keep track of this here. We got 3 and negative 1 for the midpoint of this diagonal of AC. That's going to be 3 and negative 1. Now let's find out what's the midpoint of BD. What's the midpoint of this diagonal going to be? Well, let's label this x1, y1. Let's actually erase these not to confuse ourselves. So we got x1, y1 here. We'll label this as x2, y2. So we'd have 4 plus 2 divided by 2, and then we'll have y1, which is 2, plus negative 4. That's going to be divided by 2. Notice, what do we get? 6 over 2. 2 plus negative 4 is like 2 minus 4, which is negative 2. That's going to be over 2. So that would end up being 3 and negative 1. So we're done that part. So showing this, that the midpoints of the diagonals are the same, that's how you show that the diagonals bisect each other. Right? So sometimes you'll get questions with certain quadrilaterals where you only have to show this. It'll say verify that the diagonals bisect each other. You just have to find the midpoints. You have to show that the midpoints of both diagonals are the same. And so we know it's that same point right here. This is 3 and negative 1. That's cutting this in half, cutting that in half right there. All right, but then if you need to show that the diagonals bisect each other at right angles, well, then we got to add in this other step over here. So then what we're going to do is we got to find the slopes of both of these. So let's first find the slope of AC. That's the slope formula. Or you know what? Let's first find the slope of BD, since we already have the x1, y1, x2, y2 labeled. Okay, so the slope of BD would be y2, which is negative 4, minus y1, which is 2, over x2, which is 2, minus x1, which is 4, which would be negative 6 over negative 2. Right? Negative 4 minus 2 is negative 6. 2 minus 4 is negative 2. Negatives cancel out. We end up with 3. So the slope of BD is 3. Now let's find the slope of AC. Right, so let's label these x1, y1, x2, y2. So we'd end up with y2, which is negative 3, minus y1, which is 1. Right? Yeah, and then we'll have 9 minus negative 3 like that. So this would be negative 4 over 12, right? Negative 3 minus 1 is negative 4. 9 minus negative 3 is 9 plus 3, which is positive 12. Negative 4 over 12, that simplifies to negative 1 over 3. So the slope of AC is negative 1 over 3. Notice, indeed, this slope and this slope, they are negative reciprocals of one another. If we take this, if we flip it, it will be 3 over 1, which is just 3, and then we change the negative sign to a positive, we end up with a positive 3. Or if we take 3, positive 3 over 1, flip it, and then change the sign, we end up with negative 1 over 3. Okay, so this, doing this work over here, we showed that the diagonals are perpendicular to each other. Okay, and so with both of these steps over here, we verified that the diagonals bisect each other because the midpoints are the same at right angles because the slopes of both diagonals are negative reciprocals of one another. And then finally in part C, we have to show that both diagonals are not going to have equal lengths. Okay, so what we're going to do is first find the length of AC, right, of this diagonal here. And remember the length formula, x2 minus x1 squared plus y2 minus y1 squared. Okay, so we already have it labeled, so we'll have x2, which is 9, minus x1, which is negative 3, that's going to be squared, plus y2, which is negative 3, minus y1, which is 1, that's going to be squared. So we'd end up with 9 minus negative 3, which is like 9 plus 3, so that would be 12, plus negative 3 minus 1, which is negative 4, that's going to be squared. So we'd end up with 144 plus 16, like that. So we'd end up with root 160. Okay, so the length of AC is, it's root 160, like that. And actually, just in case your teacher wants you to simplify exact values, you can break this down into root 16 times root 10, right? And then notice root 16 is 4. So 4 root 10 and root 160, those are the same thing. If your teacher doesn't require this, or even if your teacher doesn't require you to have exact values and they want the decimal, you can get the decimal as well. But in case they want you to do this, right, root 160 simplifies to 4 root 10. Both of those are the same thing. Okay, but let's leave it at root 160 because then it's easier to compare once we get the other one. So now we're going to find the length of the other diagonal, which is BD. Okay, so if we label that x1, y1, x2, y2, okay, we'd have x2, which is 2, minus x1, which is 4, plus y2, which is negative 4, minus y1, which is 2. That's going to be squared, so we'd end up with negative 2 squared plus negative 6 squared, like that, which would give us positive 4 plus 36, which would give us root 40. And so they're not the same length, right? BD is equal to root 40. If you want to get the decimal, that's going to be 6 point something. You can actually simplify this as well. 4, that simplifies into root 4 times root 10, which would be 2 root 10. Again, if your teacher doesn't require this, don't worry about this. This is grade 11 work, but some teachers want you to be able to do this, maybe on like a multiple choice test. This may not be one of the answers, but this may be one of the answers. All right. So either way, we showed that both diagonals don't have the same lengths. Okay, and it's because we're dealing with that case where we have a rhombus, which is not a square. But in the next video, what we're going to do is we're going to deal with a case where we have a rhombus that is a square, and that property of the diagonals bisecting each other at right angles is still going to hold for that. That holds for any rhombus. But then what we're going to see that when we're dealing with a square, that the diagonals are also going to have equal